transverse electric. Okay, so this means transverse magnetic modes. What exactly it means? Since we have, okay, in TEM modes, TEM modes, what we studied in last lecture, okay, we have taken simultaneously and the longitudinal component to be equal to 0, is it? You remember it? Yesterday we have taken both EZ and BZ to be 0, okay? So as a result we found both transverse components EX, EY, BY and BX, they turned out to be 0, okay? So that means there is no propagation of the wave, okay? So you don't have any kind of component, non-vanishing component in TEM modes, okay? But what we will do, we will take separately transverse electric. Okay, now if we impose boundary conditions in such a way that you take separately electric field to be transverse and magnetic field to be not simultaneously, okay? So then we can get some non-trivial modes, okay? One type of modes we call transverse electric, means you are having non-vanishing components. If a wave is propagating through, let's say, this waveguide, so you will be having throughout the waveguide the transverse components of this, let's say, electric field, they will be non-zero, non-vanishing, is it? Okay, and B is non-vanishing also. In the other case where you are having TM modes, transverse magnetic modes, you are having what? You start with only the transverse components of the magnetic field, okay, and there is no restriction for the electric field. Clear? Got it? Okay. So before doing that, let's try to understand the boundary conditions. So we started with the cylinder. Okay. So this is a conducting cylinder of infinite length. Okay. So so this is a hollow cylinder. Clear? So now tell me, let's say if you are having a component of an electric field that is parallel to this cylinder. Okay. So let's take a parallel component near the boundary of this very conductor. Okay, what will be the value of this field? So if I am taking, let's say, the tangential component, okay, across a conductor, what is the value? So it is continuous, is it? So the tangential components across a conducting surface are always continuous, is it? So that means yes. So that means the value of the field, if you are having a tangential component here, so the value of the field is same as the value of field here, is it? Is that true? Yes, sir. So because, okay, you need to take a continuous loop, okay? So this is the boundary, surface of the conductor is the boundary, okay? So tell me now, since the field outside is 0, what should be the value of the field here then? So that means the parallel component of the field is equal to 0. Clear? Okay, so this is an important condition. Okay, so we have, okay, component of E parallel to the surface must vanish due to the boundary condition, is it? So this is a very general boundary condition. Huh? Okay, so we will explore from this very condition. Okay, so what does that mean? So since we are considering this cylinder, okay, so this is lying along z-axis. Okay, so this is the z-axis. So the wave is propagating along z-axis. Clear? Okay, so that means, so you are having a component of the field that's along the z direction. Is it? A parallel component to the conductor is a component that's parallel to the z-axis. Clear? Or along the z direction. Clear? So if I take a unit vector, let's take a unit vector n normal to the surface. Okay, and E is the electric field. Clear? So you are having an n is a normal, so it's perpendicular to, let's say, this very surface. Okay, and E is the field. Clear? So now tell me how I can write this very condition. Tell me how I can write this very condition. This parallel component of E is 0, okay, at the boundary. So it's actually at the boundary. Huh? So this is at the boundary. Huh? So how I can write it? N is a normal vector, is it? E is some field, some vector. So how I should find the direction? N cross E. Okay. So this condition is reduced to N cross equal to 0. So this is the boundary condition what we have. So it's where? It's on the surface. Okay, this is very important. Okay, let me write. So it is on the surface. Okay, so let's take this very equation. We have this equation. Curl of E is equal to I omega by C probably B. So this is an equation we have derived yesterday. Is it true? Okay. So now let's take the dot product with N. So what I am trying to do? I am trying to figure out the boundary conditions, is it? So first I will look for the boundary condition. My guiding principle is that you are having a component of the electric field that is 0. Okay, the parallel component of the field is 0 at the surface, is it? You got my point? Not inside this very conductor, but it's where? On the surface. Okay, because we are looking at the continuity across this very boundary. Okay. So now let's take this N dot del E. Then we can impose what kind of conditions we require for this TE and TM modes. So I am just looking for the general conditions. Okay. So I can have I omega by C N dot B. So because ultimately, if you see, what we need to do for a waveguide, it is simply a kind of box, okay, for which you need to solve the Maxwell's equations. And Maxwell's equations are differential equations. Clear? If you know the differential equations, and you need to know actually the boundary condition, under what kind of boundary conditions you are solving these differential equations. Clear? So it is very important to get a physical solution for a given differential equation if you know either initial condition or the boundary condition. Clear? So then you can get a physical or a relevant solution for a given problem. Okay? That's why I am trying to figure out the boundary conditions. Okay? So once I know the boundary conditions, I can solve the Maxwell's equation. Okay? Okay. So now can I write this thing? Since this is a triple dot product, can I write it del dot N cross E? Okay? Just non-cyclic order. Okay? Can I write? Can I write it? Okay. So that's equal to I omega by C N dot B. Okay, so this N cross E is equal to 0 where? On the surface or on the boundary. Okay. So this object is equal to 0. So it implies, so yes, N dot B is equal to 0 on the surface. So we have arrived at, so that means B is transversal to N, is it? B is orthogonal to N. Okay, so that means B is flowing across this very conductor, okay, along this very region. Huh? So since N is a perpendicular vector, so B, it means B has to be in this direction. Okay. So now let's restate these boundary conditions. So I am having, okay. So now look here at this very condition. So N cross E is a component that is parallel to the conductor, is it? Parallel to the surface. Which component? Let's say you are having an electric field. Which component is parallel to this very conductor? It is Z component, because I am considering my this waveguide along the Z direction. Is it? Teacher, shall I write this very condition? Okay, like this thing. Ez is equal to 0. Okay, on surface. Can I write it? Can I write it? And okay, so let me write this way. And what another is? N dot B is equal to 0 on the surface. So this is how we write these conditions. Now let's look carefully what this N dot B means. So Okay. Okay, so you can, let's look at this end. Everybody is following it or not? Okay, good. Let's look at this end. If you remember, we have this Maxwell's equation. We have this, it's actually equation 8, yesterday's equation 8. Equation 8, let me write here from equation 8. Okay, so what was that equation? If you remember, IK, okay, B perpendicular minus I omega by C M cross E perpendicular, that's equal to nebula perpendicular DZ. Okay? Clear? So this was the equation. Okay, so now let's take n dot B, so which implies IK n dot B perpendicular minus I omega by C n dot M cross E perpendicular, that's equal to n dot nebula perpendicular dz. Clear? Now what is this n dot B perpendicular? Yes? It is 0. Is it 0? N dot B perpendicular? Okay? So what about this n dot M cross E perpendicular? So I can take this n inside, so take M outside. So it will be minus M dot N cross E perpendicular, okay? Because Ez is already 0, M cross E is equal, M cross E equal to 0. So that means I am having this n dot. So where this is all true only at the surface, okay? So what it means, since this n is the direction that's perpendicular to the conductor, is it? So it is perpendicular to the surface, so it means n dot this nebula is also what? Perpendicular to z, is it? So it is the transverse direction, so it means this kind of derivative that is normal, normal to the surface. So that means you need to take this very derivative normal to the surface. So I am having, so it's on surface. So where this partial by partial n, it's equal to n dot nebula is the normal derivative. Normal derivative means you need to take it normal to the surface. So that means this very condition. So Ez equal to 0, and you are having these two conditions at hand. Okay? Clear? Okay, so now let's go to the Maxwell's equations. So we have arrived at the boundary condition. Then we need to specify what kind of modes we can obtain from a given kind of boundary condition. Okay? You got my point? Okay. So now let's take the Maxwell's equations. Okay. So anybody has this idea? So you are having this nebula square E, rather I should say wave equations for E and B. Okay, what is that equal to? 1 by C square partial to E by partial T2. Okay, now let's write this thing. So it will be, anybody? So can I write this nebula square E perpendicular plus partial to E by partial Z2, that minus 1 by C square partial to E by partial T2, it is equal to 0. Can I write it?
Yes, sir.
Clear? Okay. So what is the profile of E? So anybody? So what is this profile of E? So it's E, we started with a wave flowing along the Z direction, is it? So this is our profile. Okay. So now what is the derivative? Z derivative. So it will be ik square. So that's minus k square. So which implies therefore nebula square lambda E, okay, minus k square, okay, E. So here you will be having minus. So what is that equal to? So Manisha, so it is what it is. So it's plus omega square by c square, like this thing. Okay. So E will be here as well. E is here as well. It's equal to 0. Okay. So or I can have nebula like this thing. So plus omega square minus c square minus k square. Vector E is equal to 0. So this is a two. If you see, this is a two-dimensional Laplace equation, or a Helmholtz equation, I should say. Okay, is that true? Is it a two-dimensional equation? Is it a two-dimensional partial differential equation? We call, if you are having nebula square, let's say, if you are having nebula square plus some k square phi is equal to 0, okay? So we call that equation as a Helmholtz equation. If this term is not there, then it's a Laplace equation. The difference between the two is only you are having this additional term here, okay? Got it? Okay, similarly we can have for B, okay, so B equation is the same way. So we can have this B equation, omega square minus c square minus k square E, that's equal to 0. So let me put the numbering for these things. So this is equation 14. Okay, so these boundary conditions I can write. So let's write the 12 here, and this is 13. Huh? Previous one is 11. Clear? Okay. So now, can anyone tell me yesterday's equation number 6? So we have seen now. Okay, look here. So what we have done till now in today's lecture? What we have done? We have figured out what are the boundary conditions, is it? And we have figured out what kind of wave equation I need to solve, is it? Is that true? In a given problem, I need to solve actually a Helmholtz equation. Helmholtz equation means like this thing: nebula square plus k square psi, it is equal to 0. Okay, while k square is, okay, let me write omega square. Let's write omega square. Okay. So while omega square is this very factor and nebula is actually nebula perpendicular. It's actually a two-dimensional equation. So I will write like this thing: partial 2 by partial x2 psi partial y2 psi plus, let's say, omega square psi is equal to 0. So this is a two-dimensional Helmholtz equation. Okay, and I know the boundary conditions, is it? So imposing the boundary conditions, I can be knowing what is the psi. Okay. What is the form of psi? Okay, and although I have already known this omega square, that's actually omega r what? So this will give me the energies of the system, is it? It's not Schrodinger equation. Do you see it? So what is the Schrodinger? The way you are writing Schrodinger equation. So it's like this thing, kind of thing, is it? You write Schrodinger equation in this fashion. Let's say y potential is equal to 0. Forget about potential. Okay? Is it true? Okay. So that means you need to solve, let's say, for psi, and this k is already known to you, is it? K contains, let's say, k specifies the energy of the system. Okay, so that means this omega square will specify me the energy of the mode. Okay? So at what energy? What is that energy? It's omega square by c square minus k square. Rather the frequencies. Energy is the same as the frequency. Okay? So what I need to specify? Psi. From these energies and psi, I will be able to know what kind of allowed modes are in the system. Okay? You got my point? Okay, so this is very general. Okay? Now let's try to specify, these kind of modes. What we are interested in. First, let's simplify everything. Okay? Let's simplify these equations. Because I need to know what is the x component, y component, and z components of the fields, is it? Okay? So then we can look at this kind of equation separately. Okay, so anybody remembers equation 6 yesterday? Look at the equation 6. So So that is ik E perpendicular plus I omega by C m cross B perpendicular is equal to the perpendicular Ez. So let's write it in the component form, this very equation, okay? Any problem? Better, yeah, problem. E perpendicular, that means you are having Ex and Ey, is it? So a B perpendicular contains Bx and By. So M is actually equal to, so what is M? So it is 0, 0, 1. Yesterday we have seen it. So now let's put it in the component form. You will get like this thing. Ik Ex minus I omega by C By is equal to partial x Ez. Okay. Then Ik Ey plus I omega by C Bx is equal to partial y Ez. Okay. Also you are having equation 8. That is of the same kind. Okay. Okay. So from equation 8 you will get these things. Equation 8 is what? I think there will be B perpendicular, it is E perpendicular, okay? So you need to figure it out what exactly it is, and here it will be BZ. Huh? So I will get like this thing, I K Bx plus I omega by C Ey, it's equal to partial x Bz, I K By minus I omega by C Ex is equal to partial y Bz. Let's call this set of equations as equation 50. Okay, now let's solve these equations for Ex, Ey, Bx, By. Okay? Now how many components are there? So you are having Ex, Ey, Ez, is it? Bx, By, and you are having 6 components at hand. How many equations are? 4 equations. That means you don't have what? A unique solution, is it? So it means, let's say if I fix now, we have fixed in the boundary condition what we derived, we fixed an Ez, is it? Okay, so that means that fixes our Bz. Clear? So if I fix, let's say Ez, let's say I know what is the value of Ez and what is the value of Bz, okay? So how many variables remain there? 4 variables, Ex, Ey, Bx and Bz, sorry, Bx and By. So you are having 4 variables and 4 equations. That means you will be having a unique solution. Clear? So that's why we need to, okay, to have a unique solution we need to impose a boundary condition. Okay? Clear? So now let's solve these equations for, let's solve this equation for Ex first. So tell me which equations contains Ex. So you are having this equation as Ex and this equation contains free Ex, is it? So this is Ex, By, Ex, is it? So from these 2 equations I can get Ex, is it? How I can get? You just multiply I omega by C, let's say, with this thing and Ik with this, okay? Then add and subtract, clear? So it is simple, Ax plus By is equal to, let's say, C, and the other equations you need to solve it. Can you do it? Can you do it? Okay, so let's solve these equations. Solving for Ex. Okay, if anybody is not getting, so just tell me. Okay, so you need to solve for Ex and, okay, from these 2 equations you will be getting Ex and By. From these 2 equations you will be getting Bx and Ey. Okay, so now you see the coupling. Look here. So you see the coupling here. So if you fix Ez, let's say, okay, Ex, By and By and Ex, they are coupled with each other. Okay, and similarly you are having Bx and Ey, they are coupled with each other. Okay, so let's write. So this Ex will be equal to I by omega square by C square minus K square omega by C partial y dz plus K partial x dz. Then you are having this Ey is equal to I by omega square by C square minus K square minus omega by C partial x dz plus K partial y Ez. Okay, so partial means what? D by dx, partial by partial x. Okay, and then bx, that's equal to I divided by omega square by c square minus k square minus omega by c partial y ez plus k partial x bz. Okay, and by is equal to I. So if you see, I have put everything in terms of this Ez and Bz, okay? Omega by C partial x Bz plus K partial y Bz, okay? Samajhama? So you can call this as equation, let's say, equation 60. So now you see, Ex, Ey, Bx, By, everything in terms of Ez, Bz, Ez, Bz, okay? Got it? Okay. So now let's say, okay, so if I, okay, now let's look here. If I know only Ez, okay, let me try to fix Ez and Bz, okay? I need to, in order to figure out what are these transverse components, I need to know only what? The longitudinal components. So I will fix the boundary condition on the longitudinal components, okay? So the rest will be determined, okay? So now let's do it. So let's take the first case. We call those as TE waves or TE modes. I will write TE mode. It means transverse electric modes. Transverse electric modes. Okay. So what are in transverse electric modes? So Z component is equal to 0. When I say the transverse electric mode, so that means you are having non-zero transverse component, and the longitudinal component is 0, and partial Bz by partial N on boundary, that's equal to the 0. Okay. So now let's substitute this partial, Ez equal to 0. Okay. Let's substitute. What I will get? So this is the boundary condition for TE modes. Okay. So now let's substitute. Now tell me. So put Ez equal to 0. Okay. Now let's calculate first Bx. Let's calculate Bx first. So which implies, what is Bx? Now tell me. So I by omega square c square minus k square. So it is simply k partial x bz. Okay. Got it? Okay. And then you are having, let's calculate Ex now. Ex is equal to I divided by omega square by c square minus k square. Okay, so it's partial x bz. Sorry, omega by c. Omega by c partial y bz. Okay. Wait a second. Is there any error? Okay, wait a second. So let's calculate By, no? Let me calculate By. So how much is that? So it is I here. It's I here. So you are having this I divided by. So what it is? K partial y dz. Okay? Clear? Okay. So let's calculate now Ex. Also, what is Ex? So it's I divided by omega square by c square minus k square. Then you are having omega by c partial y bz. Okay, now let's calculate what is partial y bz from here. Okay, so let's use. So I divided by omega square by c square minus k square omega by c. Okay, from this very equation, calculate partial by the dz. So it is, tell me. So it's omega square by c square minus k square divided by ik, okay, and then by. Okay, so now what is there for ex, which implies ex is equal to, so omega by c by. Is there any minus sign? Probably. Ck, it should be ck, c times k, because it's k square here, sorry, yes, it is k, denominator k, it's ck. Similarly, we can calculate now, okay, ey, okay, from this equation we can calculate ey. I require only this thing, so let's calculate ey. So what is that? I divided by, what is ey? So it is simply k partial x bz. Okay, so how much is that? I divided by omega square minus c square minus k square. K, what is partial x bz from the first equation here? Tell me. So it's omega square by c square minus k square divided by I k, okay, bx. So how much is that? So which implies this. Ey is equal to simply bx. Is it true? There is a gadwad somewhere. Partial x, so it's minus omega by c here. Okay, minus omega by c. Okay, so toshnu dhyan hai tha na. So it's minus omega by c, c k bx. Now see, even though if you are having Ez equal to 0, but the other components are generated by what? Magnetic field components, is it? Ex and Ey, they are related. Okay, so because of By you are having Ex, and because of Bx you are having Ey. So that means there is a propagation of the wave across the waveguide, okay, in this very condition. Okay, so we can rewrite this very condition in a beautiful form. Okay, so since you are having, okay, so now let's write this thing. So you are having actually bx and by. I can form a b perpendicular out of these. Can I form? So therefore I can rewrite these things. B perpendicular is equal to I divided by omega square by c square minus k square. Anybody? Can anyone tell me what this will be here? Like this thing. And what about this thing? E perpendicular. That's equal to, anybody? Minus omega by ck m cross b perpendicular. Okay. So in other words, you are having, so in transverse electric modes, you are having these things, or we can say the TE waves. So this is actually the reminiscent of the boundary conditions. It is the same thing, equivalent of saying the boundary condition what we have imposed. Okay, we have imposed a boundary condition Ez equal to 0 throughout the system. Okay, so when you move down the this waveguide, Ez will be 0 always. Okay, you got my point? And the normal derivative of Bz is also equal to 0. Okay, so out of that you get these are the fields. Or equivalently you can say my TE modes, transverse electric modes, are defined by this boundary condition. Okay, you can think this as the reminiscent of the boundary condition. Clear? Got my point? Samajh aawa? Clear? Okay. So now let's look at the TM modes. Okay, so by the way, look here. So this is also what? This is a gradient in the xy plane, is it? Is it true? So it's actually the perpendicular to the z-axis, this very gradient. But this is not defined on the surface. If this would have been on the surface, then it's equal to 0, is it? Samasha, on this, because by the boundary condition, on the surface, the normal derivative is equal to 0. So Samasha, you should not confuse with it with the normal derivative, okay? So let's take the TM modes, what it is called? Transverse magnetic. That means you are considering actually the longitudinal component to be 0. Only you take within the boundary condition the non-vanishing transverse components. So the boundary condition here it is Bz equal to 0 throughout the waveguide, okay? And on the surface, so on surface you take the Z component to be equal to 0. Got it? So this is how we distinguish between the two. So you can do the same analysis what I have done. Okay, you calculate Bx, By, Ex and Ey. So you will write it in this fashion. So E perpendicular will be equal to Ik divided by omega square by c square minus k square. Okay, and B is equal to simply omega by ck m plus e equivalent. Okay, clear? Got it? Got it? So these define as what? Transverse mode, TM modes. Clear? Any question? Any question? So now let's look at the wave equation what we have, is it? So we have defined at some point of time a wave equation. Clear? तो समझ आओ? Okay. So we have this very wave equation. So partial 2 by partial x2, okay, E, okay, so let me write psi is equal to E or B, okay, so let me use psi for what? E and B. So we have this kind of equation, partial 2 psi by partial y2 plus let me write this as omega square by c square psi, now it in a proper format, okay. So what is our omega square by c square? Tell me. So it is omega square by c square minus k square. This is just to derive the wave equation. Okay? Clear? Okay, now on this wave equation, how we specify TE mode? Because you are having, okay, you are having general, this is a general Helmholtz equation with a dispersion given by this thing. Okay, so omega will specify me the energy in the two dimensions, is it? So, samajh aawa? Okay, so this will give me the dispersion in this very waveguide, clear? In under these kind of circumstances. So now let's define on this side. So you can define psi. Okay, the way you are solving the Schrodinger equation, you have done it. Okay, particle in a box. Okay, it is the same kind of equation because that is, you know that. Okay, how you solve that equation? By boundary condition. Okay, let's say you are having a particle in a box. What kind of boundary condition you specify? Wave function vanishes where? At the sides of the box. Is it? At the walls of the box. Okay? Or you can be having one more condition if the derivative of psi vanishes on the walls of the box. So this is also one of the conditions. So these two conditions actually give us the either TE modes or TM modes. Clear? Okay, so let me impose these kind of boundary conditions. Okay. Now tell me what would be the spectrum of this very problem? Since it's a boundary value problem, is it? Let's say you start with an ordinary some differential equation where there are no boundary conditions imposed. What would be the spectrum in general? Spectrum, what is the energy spectrum? Eigenvalues. What will be the eigenvalues of that very equation? Let's say you are having a second order differential equation, okay? And you try to calculate what is the eigenvalues of these very differential equations, is it? Of that differential equation for given, let's say at a given x, okay? So what it will be in general? It is continuous because you are not imposing any boundary condition. Once you impose a boundary condition, so the discrete spectrum emerges, okay? So now it is a boundary value problem. That means you will be having a discrete structure. The energy eigenstates will be discrete, okay? We'll see it in a moment. An example we will take. There you will see, okay? So I will define. So TE modes are defined. The boundary condition, if I am having this partial psi by partial n, if it is, okay, on surface, if it is equal to 0, then I am having these TE modes, okay? Clear? Okay. So now I am having TM modes, psi defined on surface, okay? So these specify me. Okay, now let's take a quick example. Let's take, so this is a two-dimensional problem, is it? Let's try to solve this two-dimensional problem. Okay, forget about what we have done for the cylindrical object, okay? Ultimately, we have to solve this equation, is it? Okay, so what we have arrived at, tell me. So in a given waveguide, I am having TE modes and TM modes, is it? They are defined by these kind of boundary conditions I am saying, okay? Now let's say this is a quite general equation you have. Have we imposed it till now any kind of condition? So this is very general equation. That means you are having a waveguide. It's lying along the z-axis and your wave is passing along the z-axis, okay? Clear? So in that case, you are having this kind of differential equation. Let's think this waveguide instead of the cylinder, let's think it as a rectangular box, okay, cuboid, like this thing, okay? So you are having this as the waveguide, okay, of size, let's say, since it's in now 2 dimensions, because it's a 2-dimensional equation. I have drawn actually 3-dimensional. So you are having a particle in a box, 2-dimensional box, okay? It's okay. Let's say you are having one length is equal to A, another length is B. Okay, so z-axis is actually inside the board. Okay, so it's like this thing. You got my point? So you are considering only 2 dimensions. Other direction is given by. So the wave flows across that. Okay. So now tell me, if you are having a Schrodinger equation, let's forget this kind of thing. You are having a particle in a box, 1-dimensional box, okay, of length L or length A. You solve the Schrodinger equation. What is the Schrodinger equation? Is this the Schrodinger equation? Okay, forget about that H cross and everything is taken care by this K, okay? So is this the equation you solve it? So now tell me what is the solution? What is the solution of this very equation for this box? So you solve actually, you are solving this thing. Partial 2 by partial x2 is equal to minus k square psi. So your psi is actually some constant, normalization constant, sine of n pi by a x. Is that true? And you know what is the energy? So energy eigenvalues are simply, so those are n square pi square h cross square. Is that true? Divided by a square. Forget about that h cross square by 2m, is it? So ultimately the energy is like this thing, n square pi square by a square. It is in 1 dimension, clear? Now if you are having 2 dimensions, what you do? You make a separation of variables, is it? You solve it for, let's say in 2 dimensions, you are having out the 2-dimensional box. You make separation of variables, you solve it for 1 dimension and solve for another dimension. What will be that? So you must simply multiply sine of n pi by ax, sine of, let's say, m pi by b y. Why b is the this depth. Okay? So is this the case? So what is the total energy? You just sum over the along. So the energy will be simply equal to n square pi square by a square plus m square pi square by. Is it? Okay, so what is the energy? Okay, corresponding to energy, I am having this factor, omega square, is it? So much on? Clear? Okay, so now if I am considering let's say the waveguide. Let's consider a waveguide like this thing. So a two-dimensional waveguide, because it's a two-dimensional this thing. Okay, clear? It's a two-dimensional equation. I am solving it over a rectangular box. Okay, of width A and height B. Okay, clear? So now tell me, I can solve this equation. This equation can be solved, therefore solved by separation of variables. Okay, so what is this? Okay, so you can write this psi is equal to sum x of x and y of y. Can you do it? So it's very simple now. What will be now? Therefore, I can write this psi as psi of xy. What I can write? Some normalization constant. Let's write c. Okay, c is a normalization constant. Sine of n pi by ax, sine of m pi by by. So let's put n and m on this. Okay, so this is the wave allowed energy state or the allowed mode in this very box. Clear? You got it now? You got it? Huh? So what is the energy? So this object is the energy, is it? So we call this as energy. So which implies this omega square by c square. So that is equal to now, tell me, so it is n square pi. Okay, so in other words, what you can do, if you are not able to solve it by separation of variables, take this very objective, okay, take this very solution, plug in this very differential equation, okay, so this equation will be solved only if omega square by c square is equal to like this thing. Okay, so this will give me the spectrum. Clear? समझ आया? Okay, what I mean, okay, so if you are not able to solve this differential equation simply, if you are not able to solve it, so let me assume this is the solution of this very differential equation. Clear? Plug in this object, this solution in this differential equation. This equation will be satisfied only if omega square by c square is equal to this thing. Clear? Got it? But omega, what is our energy? We started with frequency. It's omega, small omega. Clear? So we need to figure that. So in this very box, so okay, so let's figure out the lowest energy mode. Okay, so let's take this thing. So let me write this as omega n m now, because it will depend on n and m. So my omega square n m by c square, it's actually equal to omega square by c square minus k square. Is it true? So what is our k? Let's calculate the wave vector k square. So it's omega square by c square minus omega square n m by c square. Clear? So wave vector gives actually the momentum, is it? So that means it will help you to propagate along the z direction, let's say. Okay, now tell me, so there occurs actually the minimum frequency, minimum of omega, this capital omega, omega nl. So at which this k goes to 0. What is the value? When omega is equal to omega nm, is it? So that means it gives you the minimum value of the frequency at which this k vanishes, is it? So, you got my point? Okay, now if this omega, okay, if this object is larger than this very object, in what case, what will happen to this k square? K square will become negative. Okay, so what is our wave first? So our wave is e raised power I k z minus omega t, is it? So this is our wave. Okay, and what is now the relation between k and omega? This is the relation between k and omega, okay, in the waveguide. Clear? Now let's say this, okay, omega square is larger than this capital omega square, because c square is in the denominator. Clear? What it means? K square is less than negative, implies k is imaginary. Okay, so it is, let's write k is equal to I k. Yeah? Clear? So what will happen in that case? So let's look at this very wave. So this k will go as I k, it's e raised for I, okay, k z minus I omega t. Okay? Is it? So what it is equal to? E raised power minus kz, e raised power minus I omega t. So what is this wave? This actually, okay, as long z increase, as the wave goes along the down the waveguide, okay, that means as z increase, what will happen to this very factor? It will decrease. That means it will reduce to 0, is it? So such waves are called waves. Evanescent waves. So this phenomenon is known as evanescence. Okay, so that means you are having certain type of waves which will damp out in the, so although it's actually always existing in the background. Okay, so think of this. Okay, let me give an example. You look through the hollow pipe. Let's say when you the hollow pipe is short, so you can look across that very pipe, is it? But if the length increases, what happens? Can you look at the end? Although your waves, EM waves go through, the light goes through that very thing, but what happens to that? It damps to 0. So the field remains there. Okay, so but you are not able to see it. So we call those as evanescent fields. Okay. So that means, okay, so any kind of propagation you require, okay, the minimum what you can have, so omega square is equal to, so the minimum value of frequency, value of omega occurs at, so let's write that omega minimum, so that's actually equal to omega square. What is the minimum value of this thing? So that means mn, it's minimum. So where to put? So let me write omega minimum. Okay, it occurs at the, what is the omega square is equal to omega minimum. Now let's look at this very formula. Why, when the minimum occurs and non-zero minimum, then m is 0, m is equal to 0. So that is trivial thing. Okay, so that means the minimum of this thing. So omega minimum is actually equal to, okay, what is that equal to? So that is simply equal to omega 1 1. Okay, so how much is that? So that's pi square by a square pi square. So that means this is the minimum amount of frequency you require. Okay, so for the wave to propagate. So this is the minimum frequency of the mode. Okay, which can propagate through the waveguide. Clear? So you got my point. Okay, so how much is that then? So now let's calculate. So I am done. So it's almost done. So what is now omega minimum? So that is root of pi square by a square plus pi square by b square. So this is the minimum frequency, okay, or the minimum energy of the allowed mode, okay, and this kind of thing. Now let's calculate. So you are having now so let's go to this very formula and calculate. So let's calculate the phase velocity. Okay, if you are having a single wave, okay, so what is the phase velocity? Let's write it as ph. So that's omega by k. How much is that? So it is c root of, sorry, c into 1 minus omega square by omega square raised power minus half. Okay, so just calculate omega by c. So you calculate omega by c and you will be getting this thing. Okay, and you calculate now the group velocity. So that means the velocity of the signal. So that's very important. So that's how much? D omega by dk. So that is c times root of 1 minus omega square by this omega square. Now look here, phase velocity is greater than the velocity of light, and it has no significance. Okay, and group velocity is always less than velocity of light, and it will approach the velocity of light only when omega is equal to this capital omega. Okay, so in that case you will hang it equal to velocity of light. So what is now the product? V phase V group velocity, how much is that? It is equal to c square. Isha? It will be c square. Because It has to be, dimensionally it is correct. So how much time is remaining?